lecture, we derived this heat equation, which is the equation of the transient temperature of a rod connected on the left and the right at two heat sources. Okay, and what we want to do is we want to approximate that equation using now that green thing is going to go down here again. We're going to approximate this. Now we need the following schematic. So along the x-axis we have x, along the y-axis we have time. Okay, we're going to be approximating the differential equation at a certain point, and this is going to be, the point here is current in distance and current in time. Up here is next in distance, sorry, in time, but it's the same in it's next in time. This temperature is next in distance, same in time, and this temperature is previous in distance, same in time. Okay, so I'm saying that if you move along the x, that's moving along the rod, and moving up and down is a change in temperature. So what we're going to have here is a notation that works like this. So this is going to be the temperature at a point I in terms of distance, and what it means, I in terms of distance means I times delta x. That's written down below. And then in time, this is L. So everywhere along this line, this central line, is x equal to xi, which is I delta x. Okay, this point here is x equal to xi plus 1, which is I plus 1 delta x. And this is x equal to xi minus 1. This line here is t equal to L, and this line up here, well, the horizontal line that's not drawn, is L plus 1, which means L plus 1 times delta t. Now we choose the delta x when we chop up the rod, and we choose the delta t when we chop up the time. So in the same way, this is going to be t I, but look at the time, L plus 1. So that's next in terms of time. Then what about this one? This is ti plus 1 because it's next in terms of distance, same in terms of time. And this one is previous in terms of distance, same in terms of time. And what this is really, you can see it's connected with partial differentiation, because if you move along the bottom horizontal line, time is kept constant, and that's exactly what a partial derivative with respect to distance needs. And if you move along the vertical line, when time is changing, distance is kept constant, and that's exactly what you want with a partial derivative of temperature with respect to time. Okay, so what we're going to do is we're going to write down our little formula again from down here. So it's k times second derivative, that won't do, second derivative of temperature with respect to distance is equal to derivative of temperature with respect to time. And we're going to use the green formulas to approximate this. Okay, so approximating the thing on the left hand side, so we'll fix our k, and now let's approximate the second derivative using the formula in the top right hand corner. And we're approximating this, so we're trying to approximate this at distance xi time TL. I'm going to have to slightly change this because this should be TL plus 1. This should be TL. And then just the TILs and stuff is just a notation. And really what it means is like TIL means I delta X's from the left and L delta T's from the initial time. So we're trying to approximate this equation at this point, and it's a point in distance and in time. Okay, so let's approximate the second derivative using the formula up in the top right hand corner. Now, it is a derivative with respect to x that we're looking at. And that means when we talk about next, current, and previous, it must be with respect to x. It must be along the x-axis, along the horizontal line. So what is the next temperature from the point we're looking at? It's Ti plus 1 L. So this thing here is next in terms of x, next with respect to x. This is current in any language, and this is previous with respect to x, and this is next with respect to time. Okay, so we've got the next minus twice the current. So the current with respect to x, well, it doesn't really matter if it's time or x, because it's current with respect to t and x, is t I L, plus the previous with respect to x is t I minus 1 L divided by delta x squared. Okay, equals, now this is really an approximation of the heat equation, which we've seen in the last set of lectures. Now, what about the derivative with respect to time? So we're using the formula in the middle up the top. So the derivative of temperature with respect to time is next in terms of time. That's T I L plus 1 minus current with respect to time, T I L over delta x. Well, here it won't be delta x, it'll be delta t, because we're differentiating with respect to t. So this is an equation that gives a relationship between these four temperatures. Now, if you think about what's going to happen, we're going to know the initial temperature of the rods. Now, if you want to think at the very, very start, see along the bottom, the horizontal line, think of that as the initial temperatures. And what this equation here does is it expresses the temperature at the middle point at the next time in terms of the previous times. So what that means, the temperature at the previous time. So what you can do is you can take the current times, temperatures with respect to time. So that's all the things along, like if I just, I'm going to scribble this out. So with respect to time, these are all the current time. And you can use them to find out the temperature at the next time. And that's what this equation down here does. So we want to solve this for this. This is the temperature at the next time. So what I'm going to do is I'm going to multiply both sides by delta t. And I'm going to swap them around as well. So carefully multiplying both sides by delta t. So I get t I L plus 1 minus t I L, with the L in the wrong place. Okay, equals k by delta t, because I multiply both sides by delta t, over delta x squared times t I plus 1 L minus t I L plus t I minus 1 L. And if I add the TIL to both sides, what do I get? TIL plus 1. So the temperature at x equal to xi at the next time is equal to the temperature at the same point at the previous time plus this k delta t delta x squared times ti plus 1l minus 2til plus ti minus 1l. And what I would say is that this is very, very, very similar to next is equal to previous plus some kind of step size times slope. Now, I don't think you can draw the exact analogy or anything like that, but it's not a million miles away. Look, next is equal to previous plus, it's not exactly step size, but some kind of generalized step size times that yoke, whatever that is. Yeah, so that's the formula we're going to use. Okay, so we got the heat equation, we derived that using theory, and then we approximate the heat equation using finite differences, and this is what we get. Okay, so the only thing I think I have to remember that I might forget is the k delta t over delta x squared. I'm just writing that down for myself. Okay, see, basically what happens now is, if you look at this equation, the things on the right, say you go at the very initial time, you know all the temperatures on the right at the initial time, because you know the initial temperature of the rod. And what you can calculate then is the temperature at the next time. Now, one thing we have to say here in contrast to, say, Laplace's equation, in terms of time, these all have to be old with respect to time, all old variables. So with Laplace, you could just write them as they are, you know, if you're using Gauss-Seidel, but for the heat equation, it does not work. They are all old because they're the current or previous time, depending on how you're thinking about it. All those yolks are L's, by the way. Right. So this equation can be written for all the interior nodes on the rod. So you go back, you've chopped up your rod into loads of little pieces. Well, for us, maybe 4, say 1, 2, 3, that's only 3. And you write that equation for each of the 3 points on the rod. And then off you go, basically. Okay. Then provides an explicit method to compute values at each node for a future time based on the present values at the node and its neighbors. This parameter lambda is important. It has to be kept small. Now, if the lambda is bigger than 1/2, it mightn't work. So you should be expecting to see the temperatures go towards equilibrium, and they will do that as long as lambda is less than 1/2. If it's between 1/2 and 1/4, what might happen is the temperature, like say it starts at 0 at a certain point and it's supposed to reach equilibrium of 50. It might just happen that like it jumps from 0, say 0 is the initial temperature. It might jump from 0 to 30 to 55. Do you understand? It's jumping over the equilibrium. So that's obviously not very good. Now it's stable. It will converge to the thermal equilibrium, but like they're not very good. You really want it to be under 1/4. So basically what I'm saying is if you have it, say, in between 1/4 and 1/2, you're going to have oscillations. So the temperature, it'll look like it goes above equilibrium, below, above, below, below, above, below, etc. And you have these oscillations, but you're getting closer and closer to the equilibrium. You're better off to have this lambda less than 1/4 for no oscillations. Now you do control lambda to a degree. You don't control K, but you can control delta T. You can make delta T smaller, is basically how you do that. Now you could make delta X bigger, but then if delta X is big, this approximation is bad. So ideally what you want to do is you want to keep delta T small and delta X small as well, and that causes an issue that we might touch on a little bit later on. Okay, so here we go. So use the explicit method, this is called the explicit method, by the way. There's an implicit method, but we won't be looking at it, to approximate the temperature distribution of a long thin rod with a length of 10 meters and the following values. Okay. Right. So let's mesh the rod. So mesh means cut it up into pieces. 0, 10, and we're doing a delta X of 2 meters. So that's 2, 4, 6, 8. Okay. And we've got delta T, we'll deal with that later. So this is 2 meters, 4 meters, 6 meters, 8 meters. In terms of the notation, though, this is going to be T1 at a certain time, T2, T3, T4. Okay. Now look at the last thing. It says the temperature at any distance at time equal to 0 is equal to 0. So the initial temperature at all of the distances is 0. So yeah, so initial temperature initially at 0, and presumably that's Celsius or something like that, because as soon as you, like I said about the specific heat capacity, but I think you can mess the equations around a little bit to use whatever units you want because it's rate of change. So I think it works okay, except now this isn't great. So this should be T0 T equal to 100 and T0 10 T equal to 50. Now what that means is at the distance X equal to 0 at any time the temperature is fixed at 100. And over here at temperature distance equal to 10 at any time is kept at 50. Okay. Now I wonder, will we be looking at the, yeah, we'll look at, it's easy to calculate the thermal equilibrium. We'll do that a bit later on. Okay, so let's draw our schematic. Don't know, what are we going to do here? Sorry. Okay, so yeah, let's draw the schematic. So this is kind of something that, well, because it's bookwork, I'm not sure, like normally in a normal year, you'd be kind of asked to do all this yourself. So this is TIL, T, same distance, next time. Down here, same time, previous distance. Same time, next distance. Now, what are we going to do? Okay, so with the heat equation, which says that K times the second partial derivative of temperature with respect to distance is equal to the derivative of temperature with respect to time. And we will also be, so we're going to be approximating that the second derivative is approximately, yeah, I think I might have equals when I really should have no, they're approximately. So the second derivative here, so using these green formulas, so I'm writing something down here that's supposed to be considered at this point, and we're looking at with respect to x. So the next thing with respect to x is over on the right. So this is the next Ti plus 1L minus twice the current TIL plus the previous Ti minus 1L. And look, all the times are the same. L delta T's. Reminiscent of, precisely because partial differentiation, you're keeping, with respect to x, you're keeping time constant. Over delta x, which is, well, we know here's 2. Don't we know it's 2? Yeah, because delta x is 2. And also we have that the derivative of temperature with respect to time is next. Now, what's the next thing with respect to time is TIL plus 1 minus TIL is the current over delta T. Do I have a delta T? It's 0.1 seconds. Okay, so I'm going to approximate this thing. I actually know what K is as well, don't I? K is 0.835. Okay, so I'm going to put both of those, this in here and this in here, to get some kind of an equation. So let me just double check the K, 0.835, yeah. So I get 0.835, putting in the second derivative, Ti plus 1L minus twice Ti L plus Ti minus 1L over delta x squared is equal to Ti L plus 1 minus T. So I'm basically just rederiving what we did a second ago over 0.1. And I need to solve this for this yoke, the temperature at a point along the rod at the next time. Now I'm going to skip the lines here. But what you get is, if I multiply both sides by 0.1 and add TIL, I get that TIL plus 1. So the temperature at a point at the next time is equal to temperature at the point at the previous time plus, so I'll have 0.835 by 0.1 divided by 2 squared. Now that's certainly less than a quarter, because 0.835 by 0.1 is 0.08 and it's been divided by 4, so it's like 0.02, so that's good. And then the stuff from the previous page, or actually just above there, Ti plus 1L minus 2 TIL plus Ti minus 1L. So that's what we're looking at. Okay. Okay, so now we're going to use that formula to, I'll see if I can get a nice value for the lambda that's a bit nicer. 0.835 by 0.1 divided by 4. 167 over 8,000. Do not introduce additional rounding error. So lambda is equal to 167 over 8,000. Certainly less than a quarter. Okay. So we've got temperatures, 4 points rather, 1, 2, 3, 4, and we're going to calculate the temperature after 0.1 of a second and then after 0.2 of a second. That's what we're going to do. So here we go. So T1, so at the first point, at the first time, is equal to the previous temperature. Now we said they all the interior temperatures started at 0. So this will be 0 plus, I'm just going to write lambda here, it's this 167 over 8,000. Now the next temperature over is 0, the current temperature is 0, plus let's look at the previous temperature. Now the previous temperature in terms of distance to T1 is over on the left here is the 100. So you're going to see a flow of heat from the end point on the left to T1 here. So this is equal to, I think we'll use 5 significant figures. So lambda times 100. So 5 significant figures. Actually, there's no approximate here. This is equal 2.0875. Now, if you look at the next point and the point after that, so looking at T2, so the next temperature at that point, x equal to 4, the second point over, it's going to have to be 0 because there wasn't enough time for the heat to get from 100 or to get from 50. So like look at the formula for T2. It's given in terms of T2, T3, T2, T1, but at the previous time, they're all equal to 0. So like the initial T1, the initial T2, and the initial T3 are all 0. So the next temperature, T2, is also going to be 0. So there's no real point calculating those. T21 is equal to T31 equal to 0 as previous, adjacent, all equal to 0. So you're just going, you can use the formula, but you're just going to get 0. Now what about T4? T4 at the next time is the previous T4, which is 0, plus the lambda, which is this 167 over 8,000. The next point over from T4, and the next point over from T4 is the 50, the heat source. So 50 minus twice T4 is at 0, plus previous is also 0. So you're getting lambda by 50. So that's 167 over 8,000 by 50, which is 1.04375. And that seems to be, now I could round that if I wanted, but sure, life is too short. It's 6 significant figures. Now let's go to the next time. So we might just write down what we have now at t equal to 0.1. So t equal to 0.1, we have these points. This is at 100, 2, 4, 6, 8, and this 10 is at 100. Sorry, this one's at 50. So this is at 0, this is at 0, this is at, I'm just going to write 1.04, and this is at 2.09 after 0.1 of a second. So now obviously the heat actually does get into the middle already, but this, like, obviously you've got errors. If you pick a smaller t, say t equal to 0.05, 2.09 and 1.04 might be relatively accurate, but the two interior nodes will have picked up some temperature at that time. Okay, so let's go again using the same formula. So we get T1, 2. So the 2 refers to the time after this. So this is t equal to 1, that's L equal to 1, delta T, and now we're looking at 2 delta T. So it's the previous temperature 1, which is the 2.09, plus the lambda, which is that 167 over 8,000, times the next temperature, which is still 0, minus twice the current temperature. Actually, I shouldn't be using 2.09. I'm actually going to be using this number here. So that's 2.0875 plus what does the formula say? The previous, and the previous to this one is the 100. And so we get out, and I'll round this to 5 significant figures. So I get 2.0875 plus 167 over 8,000 times 100 minus twice 2.0875. And 5 significant figures, I get 4.0878. Now, if you look at the increase in temperature, it's slightly smaller. So last time it was about 2.09 and this time it's about 2. And the reason it didn't increase so much is because the difference between the 100 and T1 is a bit smaller. And we know that the heat flow is proportional to the temperature difference. So when the temperature difference gets smaller, the heat flow gets smaller, the change in temperature gets smaller. Now we'll do the next one, T2, at this next time, is the previous T2, which is 0, plus lambda. The next temperature over here is 0. The previous temperature, the current temperature is 0. And the previous temperature, now we're looking at this point here, you see now. The previous is the 2.0875. And so what do we get? We get lambda, which is this 167 over 8,000 times minus, well, zeros and they're nothing, times 2.0875. And I get a little bit of heat transfer, 0.43577 if I do it to 5 significant figures. Now there's only a small heat transfer here because there wasn't much heat around x equal to 2. It wasn't that hot. So that's what that is. And now let's look at T32. Now because the left-hand side is hotter, 100 versus 50, we're expecting this number to be smaller. So the previous temperature tree is 0 plus the lambda. The next temperature over is at 1.04375 minus twice the current plus the previous with respect to x. And we'll go at this with 5 significant figures. So that's 167 over 8,000 times 1.04375. And I get 0.021788. And now we'll do 2,4. So this one we should expect to be something like 2.04. We don't expect it to increase as much as it did last time. So it's the previous temperature, 1.04375 plus lambda, which is 167 over 8,000. The next temperature over is 50 minus twice the current temperature is this 1.04375 plus the previous temperature. Now we always use the previous time. So in VBA, you have to use old variables. Let's calculate this. I get 1.04375. I'm going to put that in as an answer. So answer plus 167 over 8,000 times 50 minus twice answer. And I get 2.0439. And as expected, the temperature increase was slightly smaller. So you wouldn't do much more than that by hand. You go into VBA. So there's another question here about what is the thermal equilibrium. So what is this all going towards? So, well, we can do that with a picture fairly quickly. Temperature, distance. So we know that if you set the time derivative equal to 0. So you've got 150 and you know that it's a straight line. And you can just write down the equation of the line fairly easily. So t is equal to m. So the slope is the rise over the run. The rise is minus 50 and the run was 10, so that's minus 5. X plus c is 100. So it's minus 5x plus 100. So we're looking at x equal to 2, which should give us 90. X equal to 4, which gives us 80. X equal to 6, substitute into that, you'll get 70. And this one you get 60. So it decreases at a constant rate. So that's how you calculate the equilibrium temperature. Okay. And then what have we got here? So convergence means that as delta x and delta t approach 0, the results of the finite difference technique approaches the true solution. So, so when you're calculating these temperatures, so look at these numbers here. They're not very accurate because the delta x isn't very big. Sorry, the delta x is big. But if you theoretically made the delta x to be smaller and smaller and smaller, and the delta t to be smaller and smaller and smaller, now you have to be careful because you have to keep the lambda less than a quarter. Now you can have lambda equal to a quarter with very, very small delta x and delta t. And what that means is that these numbers on the right will be very, very good approximations of, for example, this is supposed to approximate the temperature at a distance of 4 and a time of 0.2. That as you make delta x and delta t very, very small, while keeping lambda small at the same time, not easy, that these calculations become more and more accurate. That's what convergence means. Okay, stability means that as you go on, the difference between, so the errors don't get bigger, so the errors actually get smaller. So what I'm saying there is, once you get towards equilibrium, those answers, while they might have been inaccurate initially, begin to get more and more accurate, because as you get to the terminal equilibrium, the true solution gets close to the terminal equilibrium, and so do your approximations, and it's fine. There's a small thing if you work with lambda equal to a half. Okay, so this will say that T I L plus 1 is equal to T I L plus a half, and if lambda is equal to half, T I plus 1 L minus twice T I L plus T I minus 1 L. And if you tidy that up, you actually get Ti plus 1 L plus Ti minus 1 L divided by 2. Okay, because what happens is, look, you've got TIL minus a half Ti. So basically these guys end up cancelling out with the half, or they equal to 0 to half. So this is actually the Jacobi method. Basically you're saying, remember with the Jacobi method, it was on a plate, and you said that, well, before the Jacobi method, the Laplace equation, the difference equation, just said that the temperature was the average of the adjacents. Now this is just saying that the next temperature on the rod is the average of the two adjacents. So, but it's using the old times. So this is in fact the Jacobi method. Now, so because it's using the previous times. Now what that actually means is that if you work in 1D, if you work in 2D, okay, then the Jacobi method, so 2D plate, I'll be sending a long thing, a blog post with this. Basically what happens, if you say start all the temperatures at all of the places off at 0, and you use the Jacobi method, so this is you're finding the equilibrium temperature on a plate. If you use the Gauss-Seidel method, the calculations as you get closer and closer to equilibrium mean nothing, but the Jacobi methods do. So it turns out that the intermediate things are approximations at x, y. I'll be in trouble here so we got k delta t delta x squared equal to a half. So solve that for delta 2, you're looking at something like delta x squared over 2k. So what I'm saying is, when you use the Jacobi method to approximate the equilibrium temperature on a plate, the intermediate calculations do actually mean something. That is actually the plate heating up from, say, for example, 0. It can happen, however, that errors oscillate with such a large lambda, because this is lambda equal to half. So what that means is your temperatures might you might see waves in your solutions, or so you get all weird stuff that isn't accurate. Even though they're approximating something, they're not doing it very accurately. Getting the lambda less than a quarter is very, very difficult. Like if you want to half delta x, and if you want to make it more accurate, you'll have to, I think, make delta t 4 times smaller because of the squaring. And that means if you're making delta t 4 times smaller, just 4 times as many calculations in time, and delta x and a half, you've got twice as many points. So you're increasing the computation time by a factor of 8, which is very, very difficult. So that's everything, and we're done.